Hello, this is Rohan-Paul. Very welcome to my machine learning and deep learning YouTube channel. Let's get started.
Hey everyone, so in this video I will be implementing 4 machine learning algorithms from scratch with pure Python, and these algorithms are GridSearchCV, RandomizedSearchCV, chain rule in backpropagation of a neural network, mathematical derivation of it, and neural network implementation from scratch in pure Python. Now for each of these I have separate individual videos in my channel, but I just thought putting them all together in a single video may be useful for some. And definitely I will share all the codes and related stuff in the description of the video, so enjoy. Hello everyone, this is Rohan and welcome to my channel. So in the last video I did the conceptual fundamentals of k-fold cross validation, and in today's video I will implement GridSearchCV, which is one of the primary methods to implement k-fold cross validation to find the best hyperparameters for your model. Now, before we move on, a quick word on my YouTube channel that I plan to upload videos quite frequently. So if you have not subscribed yet, please do subscribe. And if you like the video at the end, do not forget to hit the like button. All right, now about GridSearchCV, this is the exhaustive search method with k-fold cross-validation. And it pretty much moves through the each values of every hyperparameters that you pass to it and ultimately gets you the best hyperparameters or the most optimal hyperparameter for which your model performs best. That is, accuracy of your model is optimal. And then you can run your final model with that value of those hyperparameter. But the problem with GridSearchCV is that because it's an exhaustive search, that is, it checks the whole model training for each value of the hyperparameters of all the hyperparameters you provided. It's very much CPU intensive and computationally intensive, and of course that means time consuming. So for large data sets, and if you have many hyperparameters, sometime it may not be the most optimal selection to choose to find your best hyperparams. But anyway, in this video I'm going to implement the GridSearchCV, a custom version. That is, I will not use this Sckit-Learn GridSearchCV that you can see right now on my screen. So this is a much simpler version, but just to check, just to understand that how the k-fold cross-validation actually gets implemented in a GridSearchCV concept. So in this implementation, I'm only going to accommodate k nearest neighbor as a model, and so this function that I'm going to build right now is not going to accommodate other algorithm like XGBoost or LightGBM, random forest, etc., because in that case the function needs to be much more exhaustive, and it will become a much more larger project in itself. So anyway, that's the plan of today's video. Now let's jump in. And here I'm starting the code for writing GridSearchCV from scratch with pure Python. First, these are all the standard libraries that I'm importing. The one to note is this one, make classification. With this one, I will create a data set randomly created from a particular distribution, and the others are all standard: train, test, split, standard scalar for standardizing my data. I'm importing NumPy TQDM for visualizing the process while a long loop goes on, so it will show me a sliding bar, a progress bar indeed, and yeah, and the random module of Python. So the first one I'm doing is I'm creating a data set, manually creating a data set with this make classification method. I could of course take some already available data set either from some university library sources or from Kaggle, but here I'm just creating one data set because I can control all the parameters of the data set. So let's understand quickly what the parameters are here. Number of samples is just a number of samples, that is a number of rows that it will create. I have selected 10,000 here. Number of features are the number of columns of the features. I have selected 2 here. Informative, number informative. These are the informative, I mean, to talk basically, it's the informative features in the data set. let's just quickly look into the data set. Sorry, the official documentation of make classification. So it says generate random in-class classification problem. These initially creates clusters of points normally distributed, that is with standard deviation of 1, about vertices of an n-informative dimensional hypercube with sides of length 2 into class separator, and assigns an equal number of clusters to each class. It introduces independence between these features and adds various types of further noise in the data. So the important point is n-informative. Without shuffling, X horizontally stacks features in the following order: the primary n-informative features followed by n-redundant linear combination of the informative features. Okay, these is the most important points to note here. Look at further on the definition of n number of features and then n informative. Yeah, that's what I was looking for. This is the number of informative features. Each class is composed of a number of Gaussian clusters, each located around the vertices of a hypercube in a subspace of dimension n informative. For each cluster, informative features are drawn independently from a distribution with 0 mean and 1 standard deviation, and then randomly linearly combined within each cluster in order to add covariance. The clusters are then placed on the vertices of the hypercube. Okay, actually it's quite simple. It's represented as in a slightly a bit more technical words, but it's just actually quite simple things, that any informative features are just linearly independent features, and this is what is most important for this data set. I do not want linearly dependent features. That will be controlled by this one, that is linear and redundant. So I have set it to 0. Let's look at the definition of this one. Yeah, so n redundant is just the number of redundant features. These features are generated as random linear combinations of the informative features. So yeah, sometimes you do want that in some for experimenting with some models or some algorithms, but in this case, to keep things simple and straightforward, I have chosen this one to be 0, but the default value was 2. Okay, and the number of cluster per class. Let's look at the definition. So the number of clusters per class, okay, they have not explained in detail. So basically it just clusters in the class. So here also for our current exercise, it's best to keep it at 1. And okay, so with that, our X and Y are ready. And then I'm just applying this train test split to split my data set into X train, X test, Y train, Y test. I'm keeping stratify at yes and random state at 42, pretty standard code. And then if I print these shapes of this dataset, X train and X test, I get X train, they have given 75% of the data. That is by default, train test split will split 75% into train and 25% into test, and that's what I get here. All right, I just forgot to mention the one quick thing, which is the meaning of the stratify equal to 1 and random state equal to 42. So stratify equal to Y means that the train test split method returns training and test subsets that have the same proportion of class labels as the input dataset. So input dataset is X and Y, whatever the class level proportion were in these original dataset, the same kind of proportion will be maintained in our splitted dataset here. So that's what the stratify equal to Y is doing. And then the random state equal to 42. Again, the random state equal to 42 here, whether it's 0 or 1, that does not really matter. What matters is it's the same number. So if you don't mention the random state in the code, then whenever you execute your code, a new random value is generated, and the train and test datasets would have different values each time. However, if you use a particular value for random state, for example, random state equal to 1 or whatever it could be. For example, in this case, I have used a most commonly used value, which is 42. then every time the result will be the same. That is the same values in train and test datasets. So basically, the random state is just to check and validate the data when running the code multiple times. Setting random state with a fixed value will guarantee that same sequence of random numbers are generated each time you run the code. And unless there is some other randomness present in the process, the results produced will be the same as always. So this helps in verifying the output, especially when you have to run it multiple times. And the motivation for using random static with a fixed numerical value for the purpose of this video is that I will be using this split dataset to plot my results from the custom grid search function that I will create. And so when running that same function again and again, I want to see similar kind of plots. So that's why I have put it to a fixed number, random state. So basically, I use random state parameter for reproducibility of the initial shuffling of training dataset after each epoch. And talking further on these concept of random state, it's kind of similar to the seed concept of in TensorFlow, or the seed concept in any programming language for that matter. So you can refer to these very nice Stack Exchange discussion that I found pretty useful. The question they're asking is, should you use random state or random seed in machine learning models? And some of the great answer, like this one, it says the intuition is correct. You can set random state or seed for a few reasons. For repeatability, if you want to publish your results or share them with other colleagues, or if you are tuning the model in an experiment, you usually want to keep all variables constant except once you are tuning. Further, another answer, it says, yeah, this is pretty nice and compact, that it says setting a seed or fixing a random state controls randomness. When you want to do a controlled experiment like what we are doing currently in this video, you need to control randomness to some extent to achieve reproducibility, and by that also comparable result. Yeah, so reproducibility and comparable results between epochs, that's the main motivation of using it here. But another point to note is that I usually set the random state variable, not the random seed, while tuning or developing, as this is a more direct approach. When you go to production though, you should remove random state and or random seed setting, or set to none, then do some cross validation. This will give you more realistic results from your model. Yeah, this is an important point to note. All right, that was enough talking about random state. I prolonged this part a little bit because this is such an important concept in my mind. Anyway, now let's move on to our code. All right, now finally our grid search custom implementation from scratch. So before I start with this function, GridSearchKNN, I need a little utility function, which is this one, get random 60% indices. So the only purpose of these function is to that I will give it an array, and it will return me 60% of the sample data from that array chosen randomly. So that's what this function is doing. It's just using the random module of Python and the sample method of the random module, and it's returning me a length from the given array. That is, this is a population. Let's quickly look at the documentation of random, so it will be clear. So what all this random function does is this module implements pseudo random number generator for various distributions. For integers, there is uniform selection from a range. For sequences, there is a uniform selection of a random element, a function to generate a random permutation of a list in place, and a function for random sampling without replacement. And so that's the random module. It will so basically it will generate a pseudo random number. And let's look at the method that I'm using, which is sample. Where is sample? Yeah, here is random.sample. So this method takes two arguments mainly, population and the k, and the counts, it's I'm not passing that one. So what it does is return a k length list of unique elements.
k-length list of unique elements chosen from the population, sequence, or set used for random sampling without replacement. Okay, that's exactly what I want in this case. That is the first argument to sample. I'm passing the whole population of xtrain array, and then for the number of k, I am giving it, I want 60% of the given array to be returned, and that's what I'm using. This particular calculation here is 0.6 multiplied by the length of the xtrain, and actually it will be xtrain arr, yeah, xtrain array, and then it will return me in an integer format. I made a little mistake here. It will be small x, because that's the argument to the function small x train array. So again, this function get random 60% of the indices, all it's doing is that it's returning me 60% of the sample data from the whole population, and this is my whole population, that is the whole of x train array. And then after this utility function, my main function, which is GridSearchKNN. And the most important point to note here, that these function that I'm implementing here, it's a custom grid search, only will accommodate KNN algorithm. The scikit-learn's grid search accommodates all the other algorithm as well, like XGBoost, LightGBM, random forest, so on and so forth. But this is much more simpler implementation of the more exhaustive scikit-learn's implementation, and this one will only accommodate KNN, because otherwise this function needs to be much more complex and much more exhaustive, which will become a project in itself. So here this whole function is only for KNN's classifier. So let's go ahead. So first I'm just declaring these two variables for holding the mean of the accuracy score that I get during my calculations within each fold. So this will give me the mean of the accuracy scores from each of the folds that I will implement in the in here. So the first step is I am looping through. So mainly there are two loops. First, I am looping through all the nearest neighbors in the top loop, outer loop, and then inside it, for each number of nearest neighbor, I will loop through each of the folds in folds. So what is my folds? This is one of the argument to grid search KNN, and folds can be it's a number of folds that I want to operate k-fold cross validation with. So this can normally be 10, which is the most common number in many machine learning training, but it can be anywhere between 2, 3, 4, 5, or sometimes even 20, and so on and so forth. So this is coming from this argument, and that's what the inner loop is. And most of my calculation will go within these within this inner loop, because I have to run the entire KNN and get the accuracy score for each of the fold. So this inner fold will hold most of the calculations here. So let's take a look at it again. These in neighbors is just I have kept these exactly the parameter name which is there in the scikit-learn's k neighbor classifier. So there is this parameter in neighbors which takes integer as its input, and it's just a number of neighbors to use by default. And coming back to my implementation, again, remember that these GridSearchCV KNN, the whole purpose, ultimate purpose of this function, that it should give me the optimal k value of the k nearest neighbor. So what is the number for these in neighbors? In neighbors will take an array of list like this one that I will pass in the next cell. So in neighbors will take a whole array of list like this, 3, 5, 7, 9 up to 23 in this case. So and within this range, this function will return me what is the optimal number of the in neighbors that will give me the best accuracy score. So that's the purpose. So first, the outer loop, I am looping through the number of neighbors. So each of the fold, all this calculation will be repeated for each value of the n neighbors, and that's why it's at the outer loop. And then the inner loop starts here. I'm looping through each fold of the folds variable. So folds will be a particular integer number, which is an argument to this function. So within each fold, first I'm doing is I'm extracting 60% for my training, 60% of the sample data for my training by implementing these function that we just defined now, utility function get random 60% indices, and passing it the whole xtrain array, which is an argument to this GridSearchCV, and this function will return me 60% of the samples data from xtrain, and that will be my train indices. Remember, this is train indices. These are the indices of those sample data that I need to extract or keep separate from my training. And if by the fundamentals of GridSearchCV that we discussed in the previous video, that if my training indices are these, the cross-validation indices will be the rest of the samples data. So practically, the cross-validation indices will be whatever is left after selecting the xtrain samples. And that's why these line, take a note of this line very well. This is very important and very kind of interesting piece of code here, that I am implementing the set which will remove all the duplicates and return me all the non-repeated values from a range or list. And all I'm doing, these from the whole xtrain, this one, I'm deducting the indices already selected. That's all this line is code is doing. Pretty simple. Just from the whole list of xtrain, I'm deducting the indices from deducting the indices of the train set that has already been decided in the previous line. So whatever I'll be left with, that's my cross validation. And that's the whole fundamental of k-fold cross validation, that I will from each fold I will separate a training set which is 60% here, and the rest 40% will be my cross validation. So from each of the split, I have a training set and cross validation set, and for each fold, thereby I am I'm going to get an accuracy score. That is, I will train my KNN model on the training set and get a prediction from that trained model, and then check that how good is a prediction by calculating an accuracy score compared with the cross validation set. All right, so that was kind of the most important part within each fold. And then all I'm doing, this is because this is indices, it is not the actual array elements, it is just the indices. And now I have to select the array element from this line, which I'm doing by xtrain, and then just passing, I'm just extracting only the train indices, and same I'm doing for ytrain as well. From the ytrain, I'm only extracting the train indices that will become my labels, that is a y value for train. And similarly, I am doing the exactly same steps repeated here for my cross validation. That is, from the whole x data, I am choosing only the cross validation indices, and from my whole y cross validation data, I'm choosing only the cross validation indices. So my x, y, xtrain, ytrain, xCV, yCV is ready. So now this data is ready, my input is fully ready. Now all I'm doing is just invoking the nearest neighbor fit function. That is, I first declare the k, that is knn classifier in neighbors is a parameter, and that has to be an integer, like we just saw in here in the official documentation. In neighbor takes an integer, by default it takes 5, but it could be any integer number. So I am selecting k, and what is my k? This is this k. That, remember, from the outer loop, we are looping through each number of n neighbors, and my n neighbors are these list 3, 5, 7, 9, and so on. So my first k will be 3, next k will be 5, and so on. So that's why in the inside loop I am declaring the n neighbors to be the first k, which is 3 in this case, and then I'm applying the fit function. It will fit the data, that is xtrain and ytrain, with this k value. And after fitting, my model is ready to give me a prediction value. So I use a dot predict function of the k nearest neighbor, and this again comes from the official documentation. So this is official documentation, and if you check, there is this method called predict, and I'm in the documentation of k neighbor classifier of scikit-learn. So what my predict will give me is predict the class labels for the provided data, and that's what here it is, that I am predicting the y value for my xtrain current fold. And xtrain current fold has already been defined here when I extracted only the train indices. And so I get the y predicted train. That means my so now I have y predicted, and I also have the ground truth, that is y train current fault, which is this. So that means I'm ready to calculate the accuracy score, and that's what I'm doing. The next line, that is train accuracy score folds, which this array was defined inside here. Train accuracy score folds, it was defined inside the inner loop. I'm just updating this list with the accuracy score for this fold, and that is train accuracy score. Well, where did it go? Train accuracy score folds here dot append, and I'm making use of this accuracy score method that I have already imported at the very top. It's coming from scikit-learn again, accuracy score, and I'm just passing the actual ground truth y train fold, that is y train value, and the predicted y train that I just calculated in the previous line, and that gives me the accuracy score, and which is being appended to this array. So now I come out of that inner loop, and now that fold particular that accuracy score was determined. Now I also have to, for all the folds, that is I'm here for each k in the k nearest neighbor, I am looping through each fold, and after, for a particular value of nearest neighbor, for example say 3, after I am done with calculation of accuracy score of all the folds, I have to average it. Remember from our previous video, we have to average the accuracy score from different folds and then take a mean of that, and that's what I'm doing in this line. Remember, this is I'm already out of my inner loop. I'm already out of these loops, these folds actually. So if my fold is 5, all the 5 calculation have already been done. So I have 5 accuracy score from this inner loop, and now I have to calculate the mean of those 5 accuracy score, and that's what I'm doing here, and updating this array by I'm using numpy.mean function, and again I'm converting to np.array, because numpy.mean ideally should take np.array, and then train accuracy score folds, this list, which has been updated here. And the same for this one, cross validation accuracy score array from mean, and again I'm taking the mean and appending to this array, and finally from this function I'm returning the mean, the array which contains all the mean from different folds. So return train accuracy score array from mean and the CV accuracy scores array from mean. So that's my final return function, which is a mean from each fold. So again, remember, if my k4 cross validation, it has 5 fold, it will give me 5 accuracy, and then I will take for each fold I will take the mean of those 5, and that's what this final array will contain. That for each value of n neighbors, it will contain the mean from different folds. So let's just quickly draw the diagram just to make these concepts easy again. So here I'm trying to draw a little picture to explain what this function is doing. So the first for loop, that is here, the k into qdm params n neighbors will start with the number 3. And remember, again, these n neighbors is a sequence of numbers starting with 3, and I will pass ultimately a sequence of 3, 5, 6, 8 up to 23 or 24 to check for different values of k in KNN algorithm, because k is a hyperparameter in KNN algorithm, and the whole purpose of this GridSearchCV is to give me the best hyperparameter, that is the best value of k for which I get the best accuracy score. So this is the first for loop, the outer loop, and the inner for loop will run for different folds. For example, if I assume this will be a 4-fold cross validation, it will run for 4 different values: 0, 1, 2, 3. So this is the inner loop. This is the inner loop, that is this one for fold in range folds, and this folds is again the an argument to this function. And so if I run it for 4 folds, that means it will run this loop, inner loop, for these different folds, but for each fold it will split the data into training set, which is 60%, and cross validation, which is 40%. And it will do for the next fold as well, training CV, and the next training CV, and also the next training CV. So this inner loop, for each of these, each running of this inner loop, I will split the data into training CV, training CV, training CV, and that I'm doing through this function, get random 60%, this function. And the cross validation part is just chosen from the rest of the, after choosing the train indices from the rest of the indices, is the cross validation indices. So this is pretty much the splitting. And after each split, after this split, I will, from this split, I'm calculating these predicted value, y predicted for my cross validation, and also y predicted train. And then from these different 4 folds, I'm getting a mean of all of them, and that's what I'm doing here. And that mean I'm appending to the final. For each fold, I will get one single mean. For each run of the inner loop, I will get one single mean, and that mean will get appended to these final return value from this function. So yeah, so that's pretty much the GridSearchCV custom. Now let's quickly plot one to see the exact functioning of this. I just forgot to mention one quick point, that after I do the splitting in train and CV, what these steps are doing pretty much is that I'm running the KNN algorithm on these, I'm fitting the KNN algorithm on this train data, which is this line, fit, yeah, this line KNN CLF dot feed, and then I'm passing X train current fold and Y train current fold. So I'm fitting the KNN algorithm for the train here, for the train here, train data here, train data here, and then I'm calculating the accuracy, and after fitting it, then I will get the accuracy score. I can get the accuracy score both from my train data and also from my cross validation data, and I'm actually indeed calculating these accuracy score from both train and cross validation. Like in here, train accuracy score folds and CV accuracy score folds here, and then only then I'm calculating the mean from that.
And now finally, I'm just implementing this GridSearchCV function that we just built in the previous cell, and passing. So here I'm first importing a k-neighbor classifier from Sckit-Learn, and then declaring a neighbor variable, neigh variable, with the k-neighbor classifier class. And the params for the hyperparameters, I'm passing in neighbors, which is the main hyperparameter for KNN algorithm, and I'm passing all these values as a sequence or list of integers, and the number of folds that I want to run this is 5. So, and so here is my function. I'm only passing X train, Y train, this neighbor, params, and fold as 5. And X train and Y train has already been defined earlier here after the train test split. So this function will return me the train score and the CV score, and internally it will make the k-fold cross validation with number of folds being 5. And then to check the results, I am running these. Remember, this GridSearchCV will give me the train accuracy score and CV accuracy score mean from my custom implementation of this function. So these values are actually is going to be accuracy is, and so is this one, because I am going to plot it in the next cell. So the CV score accuracy, and I'm taking it here. I'm just in the next cell. I'm just plotting this accuracy score against the various values of k. We'll come to that in a second. Let me correct this one. Train scores accuracy. Okay. All right. Let's just run this cell. Okay, so this is, as you can see, these with this progress bar, it's running for 5 folds, and let's wait. Yeah, it's done 100%, and now
I will be plotting these accuracy score against various values of k, and we'll check that which value. The ultimate goal of this whole exercise was to get the optimal value of k. So in this cell, I'm just plotting two simple plotting. The first plot is just the train score accuracy. The second line is CV score. And here is a plot I'm getting. So the most important thing is that I have to choose a k for which I get the maximum accuracy for my cross-validation plot, but also the distance between these two peaks should be the minimum. So I can see that this is the point. This is the point which is my optimal k from this graph. It's something like, I think it's almost at 15. So 15 in this case would be my ultimate most optimal k value for running the k nearest neighbor algorithm after doing the cross validation. Because at 15, my cross validation plot is giving me the highest accuracy, and also at this point the distance between the train accuracy score curve and CV accuracy score curve is like, it's almost minimum as well. All right, so I think that pretty much wraps up this video. All right, if you like the video, please hit the like button, and also I will be uploading videos to my channel quite frequently, so please consider subscribing to my channel. All right, see you in the next video. Hello, this is Rohan-Paul. Very welcome to my machine learning and deep learning YouTube channel. Let's get started. So in the last video, I did a simplified implementation of GridSearchCV function without using scikit-learn and with pure Python. And in this video, I'm going to do the same with RandomizedSearchCV. So this video, I am going to implement RandomizedSearchCV without using scikit-learn with pure Python. And again, just like the previous video, this function is going to accommodate only k nearest neighbor algorithm, because if I want to accommodate other algorithm like XGBoost, LiveGBM, random forest, etc., this is going to become much larger project, and that is almost going to be equivalent of scikit-learn. And again, the purpose of these from scratch implementation is to learn the under the hood mechanism of how GridSearchCV or RandomizedSearchCV works, and in general how k-fold cross-validation is implemented in our training. First, a quick recap on hyperparameter tuning methods and the differences between hyperparameters and parameters. So hyperparameter tuning refers to the shaping of the model architecture from the available space. In simple words, it is about searching for the right hyperparameter to find high precision and accuracy. And the most widely used parameter optimizer techniques in classic machine learnings are grid search and random search. Now, the difference between hyperparameters and parameters. So parameters are the variables that are used by the machine learning algorithm for predicting the result based on the input historic data. These are estimated by using an optimization algorithm, for example, gradient descent. Thus, these variables are not set or hard-coded by the data scientist. These variables are produced by model training. Examples of parameters are coefficient of independent variables in linear regression and logistic regression, or the weights in neural network training. And now, hyperparameters are the variables that the data scientists specify usually while building the machine learning model. Thus, hyperparameters are specified before specifying the parameters, or we can say that hyperparameters are used to evaluate optimal parameters of the model. And examples of hyperparameters are a max depth in random forest algorithms, or the k in a k nearest neighbor classifier. So hyperparameters are not the model parameters. That's the main point. And it is also not possible to find the best set of model parameters from just the training data, because model parameters are learned during training when we optimize a loss function using something like a gradient descent. So in the grid search or randomized search tuning technique, we simply build a model for every combination of various hyperparameters and evaluate each model. The model which gives the highest accuracy wins. The pattern followed here is similar to the grid, where all the values are placed in the form of matrix each set of parameter is taken into consideration and the accuracy is noted. Once all combinations are evaluated, the model with the set of parameters which gives the top accuracy is considered to be the best. So now look at the GridSearchCV architecture. So in GridSearch, it uses different combination of all the specified hyperparameters and their values and calculates the performance for each combination and selects the best value for the hyperparameters. This makes the process time consuming and expensive based on the number of hyperparameters involved, because you are not leaving any single hyperparameter, you are not leaving any values of a single hyperparameter. That's why it is called an exhaustive search, that you are looping through each and every possibilities, each and every combination. Now compared to these, so that's the limitation of GridSearchCV, that grid search does not scale well. There is a huge number of combinations, so we end up testing for just a few parameters. For example, if we have 4 parameters and we want to test 10 values for each parameter, then there are 10 into 10 into 10 into 10, that is 10,000 combinations possible. And all right, so now let's look at the randomized search CV. So here in random search, it's a technique where random combination of the hyperparameters are used to find the best solution for the built model. So the randomized search follows the same goal. However, we will not test sequentially all combinations. Instead, we try random combinations among the range of values specified for the hyperparameter. So here initially we specify the number of random configurations we want to test in the hyperparameter space. And the main advantage is that we can try a broader range of values or hyperparameters within same computation time or as compared to grid search, or test the same ones in much less time versus grid search. But the problem is that we are not guaranteed to identify the best combination, since not all combinations will be tested. This works best under the assumption that not all hyperparameters are equally important, and which is indeed true for many classic machine learning algorithms. Both GridSearchCV and RandomizedSearchCV implements k-fold cross-validation. So let's quickly recap what that is, as in this slide. So k-fold cross-validation is the most popular type of cross-validation. It is an iterative process that divides the trained data into k partition. That is, let's say the iteration number 1, the whole data set is divided into one k different partition, and each iteration keeps one partition for testing. Like in this case, this is the testing part, and the remaining k-1 partition for training the model. So the next iteration will set the next partition as test data, and the remaining k-1 as trained data, and so on and so forth. So in each iteration, it will record the performance of the model, that is, calculate the accuracy or the precision, and at the end give the average of all the performance for that iteration. So this is the whole k-fold cross-validation in a nutshell. And now the actual code for implementation of random search CV. This is my notebook. Definitely, I'm going to share the GitHub link of this in the description section of the video. So the first is just importing some standard library. The make classification module of scikit-learn is just to create some dummy data, classification data for on which this random search CV function I'm going to test. Then a normal train test plate to split my data set, and the numpy, the random module of Python, because I'm going to we have to generate random variables for implementation of random search CV. And the stqdum package is just to show a progress bar kind of thing when a long loop goes on. So the first step is just to creating some dummy dataset with make classification, and I discussed it previously, these parameter meaning, but just quickly go through it again. So if you go to the official documentation of make classification, this generates a random in-class classification problem, and number of samples is just the number of samples, that is the number of rows. The number of features in features is the total number of features. These comprise in informative information features, in redundant features, and in repeated duplicated features. So in informative is the most important part, that the number of informative features. It is as simple as these. And in redundant, by default it takes two. That is it's a number of redundant features. These features are generated as random linear combinations of the informative features. So you may choose to have no redundant features in your dataset. That is a choice I have made for this exercise. So I am giving the number of samples. I'm generating a 10,000 samples. Number of features 2. In informative features is also 2. And I'm setting the in redundant equal to 0. That means I will have no redundant features. And number of clusters per class is 1. Random state 60. By specifying the random state, I am making this whole generation of this dataset is more reproducible. That is, it will create same sequence of random dataset each time it is run. Because when you want to test your code and you want to test the output of a function on these features and on this generated data set, you want to give a random state a particular integer, because you want your output to be reproducible so that it can be compared with one output with another output. And then the regular very famous train test split. I'm just splitting my original generated X and Y to train set and test set. All right, and if you just print the shape of this my train set, it will create 75% as train, and that's my 7,500 of training data set out of total 10,000 samples. And then just to check that how this data set actually plots, I'm just creating a very simple scatter plot, and this is my data set that I created above in the above cell. So this is how the this is going to be a classification kind of problem, because I'm implementing KNN here. That is, I want to apply KNN algorithm on to find the best K to get to apply to see how my random search CV custom function is working. And that's why this is a classification data set that I have created, and you can clearly see the demarcation of the how the data set is scattered in the space. All right. And this is a little pseudocode for the custom random search CV. And to repeat again, the whole purpose of doing the random search CV is to get the optimal K of KNN algorithm, which will produce the best accuracy for my training dataset. So that's the whole purpose here, to get the K value for which I will get the best accuracy. And this is the actual code here. And I have put actually detailed comments for anybody looking at the code to understand the flow in detail. So definitely I'm going to share these link in the description of this video. So fundamentally, to understand the flow for random search CV, that it will randomly select some values from the hyperparameter, and K is a hyperparameter here, and then with that value of the hyperparameter, it will run each fold, and all the accuracy calculation for each fold will go in the inner loop. So there will be two loops. Outer loop will move through the values of the hyperparameter, which is n neighbors in the case of KNN, and then the inner loop will loop through the calculation under each fold. So let's quickly check. And the main difference between GridSearchCV and random search CV is GridSearchCV will move through or loops through each combination of hyperparameter values and under each fold, but the random search CV will randomly select some hyperparameter values to do its calculation. That's the main difference. And this line is that line of the key defining factor of random search CV, that it's randomly selecting some values from the hyperparameter params range. So this param range in this random search CV custom function, param range is an argument into the function, and this line will just randomly sample or randomly select 10 values from this param range. So like I have put in the comment, generate 10 unique values from uniform random distribution in the given range, starting 1 to param range. For example, if param range is equal to 50, we need to generate 10 random numbers in range 1 to 50. And okay, then these classifier params here, I have hard coded it to be n neighbors, because like I said, again, this function is a very simplified version, so it will only accommodate knn algorithm, and in knn, n neighbors is the hyperparameter, and this is set equal to these randomly generated 10 hyperparameter values from the param range. And with these defined, now we will move through two loops that I was just talking about. There will be an outer loop and there will be an inner loop. The outer loop moves through these values of n neighbors, and the inner loop moves through each fold value. So number of fold, this variable is input to the function, or an argument to the function, number of total fold, and then the inner loop do all the calculation under each fold of this number of total fold. So again, the outer loop, I have already in this loop, these data of moving through the various values of n numbers will start, and then the most important loop is, of course, the inner loop, where the whole fold calculation is going on. And so let's check out calculation for a single loop. So the first is number of elements in each fold, and that's a very simple, that the total length of the X trained data set divided by the number of total folds. So if I have 100 sample and I have number of folds equal to 10, then I will have the number of elements in each fold is also equal to 100 by 10 equal to 10. And then I have to implement the most important concept of fold here. That is, I have after dividing the whole data set into k fold, I have to separate the test set, which is one single fold out of 10, and the rest 9 will be my training set. So this is what I'm doing here. The test indices, this variable will hold only the indices of the test set. That is a single set out of all the k different set of the data. So test indices is simply a group of data from starting at the start of one group and ending at the start of the next group, and that's what you can see here. The number of elements in each fold multiplied by the fold number. This is the starting point, and the ending point is the number of elements in each fold multiplied by fold plus 1. Because fold will be a successive number, 0, 1, 1, 2, 3, 4, 5, 6, like this, not 0. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Say I'm doing a 10-fold cross validation here. So my each fold, under the fold, the test indices will be a single fold, and these range will extract that single fold by extracting data from starting of one fold to the starting of the next fold. And then the rest, after I select the test indices, that is a single fold, the rest all the folds, the rest all the data will be my training set. And this train indices is doing just that from my whole X train total, it is just deducting these test indices that has already been decided here. So the whole rest of the data set is my training set. So yeah, I have put in really detailed comments here. You can, if you look into the code in GitHub, you can definitely make sense of it. And let's move on. So it is just another, again, explanation of this fold concept. So for a data set of total 100 rows, one loop of fold will have the following test indices and train indices kind of split. So in this case, I'm just assuming I have 100 rows of data or 100 sample, and my test indices, let's say I'm doing a 3-fold cross validation. So one fold of data will be my test indices. Let's say these are all those 0, 1, 2, 3, 4, 5, 6, 7 up to 24. Then all the rest of the indices will be my train indices. All right. So yeah, it's very obvious if you read it, if you read through it. And then given now, the whole flow of the code is just like what we did in the last video in GridSearchCV. That is, the structure of the code is exactly the same. So now that I have my test indices and train indices decided, I only have to extract the data from using that indices, and these 4 lines is doing just that. Pretty simply, it's doing my actual data set of xtrain, ytrain, xtest, ytest by using these indices number that has been already captured here above here. All right, so my data is fully ready. Now all I have to do is run knn and predict it and get the accuracy. And after I get a single accuracy, I have to do for all the folds and then get the mean. And that's all these 2 blocks of code is doing. So here I am still inside the inner loop where I am defining the classifier.neighbors to be k. Remember, this neighbor is the parameter, actual parameter name in scikit-learn's k neighbor classifier. These module of k neighbor classifier has an exact parameter called n neighbors, which represent the k values. And that's what I'm doing here. I'm just defining classifier.n neighbors equal to my k, and the k, remember, it's a value of this current loop that I'm running. So in neighbors will have different values, and k will represent those values like 3, 4, 5, 10, or whatever. All right, now I'm just with that k, my k is defined. Now I'm just fitting the data on xtrain fold and ytrain fold, that is this and this. And after fitting, then my model is fully trained. Then I'm ready to predict. And now my y predicted, first I'm doing on xtest fold. That's my y predicted. This is actually, I can rename it y predicted test. But yeah, let it be. I'm not editing the code right now within the video. So yeah, so first I'm doing the y predicted for xtest fold, and then I'm doing test score folds dot append accuracy score, because I have my y predicted value ready now, and my actual ground truth of y is here anyway. So now I'm ready to calculate the accuracy score, which I'm doing here, accuracy score y test fold and y predicted, and that accuracy I'm appending to this variable. I'm doing exactly the same for the train data set. And then finally here I'm out of the inner loop. So here with the final array, this train score, this is the final array, and that will calculate the mean values of each of these accuracies. So I'm just making use of this numpy mean value, np.mean, and I am appending to these final 2 variables the mean of train score folds and test score folds. And this 2 variable is the final output or final return values from this function. Yeah, so now this function is done fully. This function here, it looks visually it looks large, but it's actually very easy. It visually looks large because I have put in so much of comments here, but it's actually just, I think, maximum 15 to 20 lines of code. And now that my function is done, I am ready to test it to see how what kind of output it generates, and what kind of plot it generates, because I also want to see the ultimate motivation of doing all these, that is what is my best k, what is the best value of the hyperparameter k. So in this cell, I'm just importing k nearest neighbor from scikit-learn, and then I am defining a variable with the k nearest neighbor class and setting my params range to be 50, number of folds equal to 3. And then I'm running my whole this function that I just defined above, that is RandomizedSearchCV custom, and passing xtrain, ytrain, neighbor is this neighbor, which is k neighbor classifier of scikit-learn. Param range has been defined to be 50, number of total folds is 3. And if I print the output, I will get this kind of arrays. Remember, these array are the mean values of the accuracy. So this is the mean value of the accuracy score from train score, and the second array is the test scores. And now this is the final step, which is I just want to see if they are making sense at all by looking at the plot. So in this plot, uh, I'm only plotting the k values, that is hyperparameter k values, and the accuracy. And so we have to choose the k to be the most optimal, where my test accuracy is maximum, and also the distance between the test curve and the train curve is at the minimum. So looks like, looking at the plot, my test accuracy probably touching a max something probably here at the value of 42 or 43 somewhere, uh, as far as I can see from bare eyes, and also the distance is kind of the smallest between the train curve and test curve at this point. So for this dummy dataset, uh, if I want to apply KNN on this dataset, the best optimal K that I'm going to use is 42 or 43. That's the whole purpose of the entire random search CV. So yeah, that pretty much wraps up this video. And if you like the video, don't forget to hit the like button. And also, I plan to upload videos quite frequently to my channel, so please consider subscribing. All right, see you next time. Hello everybody, good morning. In this video today, I will go over the process of backpropagation in a neural network architecture, and how the chain rule of differential calculus comes into play to calculate the weights and fine-tune the weights. So before going into the details of the process, let's quickly go over the overall what neural network is all about. So you can already see in this photo, it's a supremely basic and supremely simplified structure of a neural network architecture. So each neuron is connected to other neurons, but not all connections are equal, and that's where the concept of weight comes into the scene. And speaking more formally, in a neural network, a firing neuron propagates an impulse of 1 to the outgoing neurons, while a non-firing neuron propagates an impulse of 0. That's how you can think of it. So you can think of the weight as indicating how much of the impulse of the firing input neuron is forwarded to the next neuron via the connection. Mathematically, you multiply the impulse by the weights of the connection to calculate the input for the next neuron, like we are doing here. I will go over this calculation in a little bit more detail in a while. So the overall structure that we have here for this example, it's a very simplified one. It contains one hidden layer, which is this, with 3 nodes in it, and one input layer and one output layer. So every arrow in this diagram contains exactly one float value as a single weight that is adjustable, and that's what we will do. That is, we will adjust the weights to figure out the least possible loss to the overall structure. So totally there are 9 weights, 6 in the first layer, 1 2 3 here, 1 2 3 here, and 3 in the second layer. So totally 9, and we have input as 1 1, and the output should be, that is we have to target the output to make it as close to 0 as possible. That's the problem here. And so when we fine tune these weights, that's what training is all about. And we have not introduced a bias value yet here, for simplicity purpose only. The underlying logic remains the same, however. So in this step, we perform the multiplication of the input with weights to calculate the value of hidden units in the hidden layer. So for example, this h11 value, which is here on the first node of the hidden layer, that is derived by multiplying wx1 with w11, x2 with w21 accordingly. And we have given some imaginary number here as weight 0.8, 0.4, 0.3. So the h11 value comes out to be 1, h12 value comes out to be 1.3, and h13 is 0.8. And the by the normal terminology, how these subscript is determined, let's see the rule here. uh, so when I said W12 or W22 or W11, the way that it is determined is that the first number in any weight subscript matches an index of the neuron in the next layer, and the second number matches the index of the neuron in the previous layer. So the weight here it's W11 because the next layer, the first node it's going to is 1, and the previous node is also 1. But this structure here, the second weight, that is here W will be 1 2 because it's going to the number 2 node in its target, and it is originating that its previous node is number 1. And now the basic question, what is a neuron? A neuron is a container that contains a mathematical function which is known as an activation function, which takes inputs as x1, x2, which is input values, and it also take a vector of weights w1, w2 in this case, and a bias term. A neuron first computes the weighted sum of the inputs like we see here, and passes it through the activation function. And what is an activation function? Activation function is simply a mathematical function that takes in an input and produces an output. Think of the activation function as a mathematical operation that normalizes the input and produces an output. The output is then passed forward into the neurons on the subsequent layers, and that's how the feed-forward motion goes on. So a feed-forward propagation's high-level steps can be summarized as below that. Number one, perform a sum product at each neuron, then compute activation function, repeat the first two steps at each neuron until the output layer, and then finally compute the loss by comparing the prediction with the actual output. And that's where one cycle of feed-forward propagation is done. And then the back propagation will start. So what we do in feed forward propagation, we connected the input layer to the hidden layer, which then was connected to the output layer. In the first iteration, we initialized weights randomly and then calculated the loss resulting from those weights values. In back propagation, however, we take the reverse approach. We start with the loss value obtained in feed-forward propagation and update the weights of the network in such a way that the loss value is minimized as much as possible. So here are the high-level steps of back propagation. That is, start at the output layer, change each weight within the neural network by a small amount, one at a time. Measure the change in loss, that is delta L, when the weight value is changed, that is delta W, and update the weights by minus k multiplied by del L del W, where k is a positive value and is a hyperparameter known as learning rate, and del L del W is a well-known thing called the gradient of loss with respect to the weights. So why computing this gradient that we just discussed in the previous steps here, that is update the weight by learning rate multiplied by the gradient. And to answer these, we first need to revisit what some of the basics of calculus, differential calculus to be specific. So gradient of a function c, in this case c is a function of x1, x2 and so on. In point x is a vector of the partial derivative of c, and that is given by like this, that is del c del x equal, that is, which is a vector of del c del x1, del c del x2 and so on. The derivative of a function c measures the sensitivity to change of the function value, that is the output value, with respect to a change in its argument x, which is input value. In other words, the derivative tells us the direction c is going, and the gradient shows how much the parameter x needs to change in positive or negative direction to minimize c. And in this case, we want to find the change of the loss with respect to the individual weights. And we'll come to that in a while. Let's move over. So how does a neural network update weights and biases during a backpropagation? And the answer is backpropagation reduces the error by changing the values of weights and biases. To do this during the backpropagation, we calculate the rate of change of error with respect to rate of change in weight. That is this term, the gradient del L del W. And note that the update made to a particular weight is proportional to the amount of loss that is reduced by changing it by a small amount. Intuitively, that makes sense, because if changing a weight reduces a loss by a large value, then we can update the weight by a large amount. However, if the loss function is small by changing the weight, then we update it only by a small amount. And those calculations, those rate of changes are all determined and controlled by this all important factor, gradient, that is del L del W, and we will calculate it with the application of chain rule of differential calculus. So now, before going into the details of actual calculation of the chain rule with differential calculus, let's understand why we need the chain rule in backpropagation at all. So far, we have calculated the gradients of loss concerning or with respect to weight by updating the weight by a small amount, and then calculated the difference between the feed-forward loss in the original scenario when the weight was unchanged and the feed-forward loss after updating the weight. That was our original proposition during the backpropagation. But one drawback of updating weight values in this manner is that when the network is large, containing thousands and millions of nodes and weights, which is very normal with real-world dataset, a large number of computations are needed, and so that becomes almost impractical in few cases. And how that happens, let's check out the actual mathematics of that. So we already understood that our loss or the cost, which is at the output layer, it's C, and it's a function of weights, that is W1, W2, W3, and so on. So you number the weights with W1, W2, and want to compute the gradient, that is a change of the cost or the loss with respect to the weights and each of the weights. So what we want to compute is del C by del Wi. It's C actually. Sorry for the bad handwriting. And the Wi represent each of the weights. It could be in millions with real-world data set. So an obvious way to do this is like below. Let's go to another slide. Del C by del Wi equal to, it will be we already know that C is a function of weight, so we are changing the weights like so. We have to update the weight by adding a small amount of weight, and then compare the difference of the cost function with the original weight. So this is what we do. We update the weight here, that is W plus adding a small amount. Let's denote it with not like this. Let's use epsilon and EI. I will explain what these terms are in a while, and deduct the original function, divide the whole thing with a small amount. So here this symbol epsilon, it's actually here it's a small amount and greater than 0, and EI above, that is this term here, is the unit vector in the ith direction. So in other words, we can estimate del C del Wi by computing the cost for two slightly different values of Wi, and then applying the gradient calculation. So this same idea can be used to compute the partial derivative del C del B with respect to the biases as well. That is when the term is del C and del B, B represent the bias here. The same kind of calculation can be performed there as well. So this approach looks very promising and simple to understand, and would not take more than 3 or 4 lines of code. But then there's a problem here, and let's understand what is that. So imagine for a real world case, we have a million weight, and so that means to calculate these terms, we have to calculate these W, the changed weight, W plus epsilon I, and W, and the entire gradient a million times. That means that to compute the gradient, gradient at the end, we need to compute the cost function a million different times, requiring a million forward passes through the network for each training example. And that's where these the chain rule of backpropagation comes to save us, because it has a specific order of operation that is highly efficient. What's clever about backpropagation is that it enables us to simultaneously compute all the partial derivative of that is del C, and del Wi using just one forward pass through the network, followed by one backward pass through the network. And so the total cost of backpropagation is roughly the same as making just 2 forward passes through the network. Compare that to a million and one forward pass with our previous original brute force method. All right, that was enough of the logic why we needed a chain rule to handle these hugely large backpropagation operations. So now let's start with the actual calculation of the chain rule. So this is our network. Going back to the original picture, that we have one input layer, one hidden layer, one output layer, and there are total 9 weights here, 3 from the input layer to the hidden layer. Sorry, 6, 1, 2, 3, 1, 2, 3, 6 weights from input layer to the hidden layer, and then 3 weights from the hidden layer to the output layer. It's a very simple structure. And the absolutely simplified for this explanation here, but practically there will be multiple hidden layers. So now the loss here at the output will be, for this example, we will consider mean squared error defined as, second. Just 1 second. Okay. We'll define the mean squared loss like this. MSC. And this is represented by the letter C here for this example only, is equal to y minus y hat whole square. And the predicted value, that is this y hat, is equal to, you remember that we already discussed that y predicted value is a weighted sum of the weights and the values at various nodes. So that would be A11 into W31. That is A11 here and W31 here, plus then I have A12 and W32. A12 into W32. Further, I have from this layer to this layer, so okay, plus A13 into W33. And remember, again, we already talked about this, that how this subscript number for the weight is determined. The first number is a number where it is going, and the second number, it is where it is coming from. So that's how this is determined. Okay, and now the hidden layer, for the hidden layer, this value A1, A12, and A13, how this is determined is for this example, we will consider the sigmoid activation function. So a one will be determined with a definition of activation function, which is 1 by 1 plus e to the power minus h11. So this is a hidden layer activation value for a sigmoid activation function. And what is my h11? That is this value. That would be the weighted sum. Again, h11 equal to x1 into w11, because my h1 is being fed by these two weights, w11 from here and w21 from here. Okay, x1 into w11 plus x2 into w21. And now we want to find out how much of an effect of a change in the weight has on the cost function. That is the rate of change of the cost with respect to rate of change of a single weight. So that we can represent with the chain rule of differential calculus. Let's do that. So what I want to have is del C by del W11, and that can be represented as a multiplication of four different differential, which are as follows. I hat into del and the final one is del h11 with respect to relatively simpler way to remember this is that each of these factor cancels out, like del y hat cancels out with del y hat here, and similarly here and here. So this is as a result of a chain rule that we discussed earlier. So essentially we are just performing a chain of differentiation to fetch the differentiation of our interest. So all these individual differentiation, that is four components, ultimately gives the differentiation that we want, which is del C by del W11. And then the question is why we are doing all these four different individual component-wise differentiation, and the answer is that we create a chain so that each individual partial derivative can be easily calculated, and thereby we get the derivatives of two variables which are not directly connected, that is del C, and that is this cost function. Change of the cost function is not directly connected with the change of the weight W11, but with this application of chain rule, we can actually connect it by individually calculating the four different components and get what we want. That is, we want the change of loss with respect to change of a single weight. And now the next task is to calculate each of these separate components differentiation. That is, we need to derive what exactly is del C, del Y hat, what exactly is del Y hat, del A11, and so on and so forth for each of these 1, 2, 3, 4 components. So let's start with the first one, which is del C with respect to del Y hat. And that we already had the equation of del Y we already have the equation y hat. So now let's do this. The first one, that is number 1, is PLC by y hat equal to, we need to calculate the loss. The loss in this case, that is, we know the value of C. Let's do this. And by replacing the value of C, we get y minus y hat whole square. And this comes to -2 into y minus y hat. And how we get this? It's just a power rule of differentiation, that is ddx of nx to the power n is equal to nx to the power n minus 1. Okay, so that one is done, and now go to the next one, which is del y hat by del A11. Okay. So del y hat will mean del A11. We already earlier saw the value of y hat, which we can see here again. Yes, so this is, earlier we discussed that this y hat, that is output value from the final output layer, is a weighted sum of all these individual values and multiplied by the weight. So let's have the same value here as well. So is equal to del A11. I'm just replacing the exact value of y hat here. Instead of the y hat, I'm just putting that value. Plus, I think that is slightly wrong here. That would be A11 multiplied by the first two, it was 3, 1. Plus A12, the second weight is W32, and the third one is A13 multiplied by W33. So if you simplify this by applying the very first principle of differentiation, you will get this value, W31. Okay, so we are done with the number 2 from our this is what we are trying to simplify. So we are done with the number 1 and number 2. Now we have to go to the third one, which is del A11 del. And remember what was our H11? That was the value derived after applying the sigmoid function. So this was our value of A11 and H11. H11 is just the weighted sum of the weights and the value of x1 and x2, and A11 is the result of applying the sigmoid activation function. So we have to know the derivative of a sigmoid function, and that we can let's forget this line for now. First see what is the derivative of a sigmoid function, and that is if sigmoid function is del x equal to 1 by 1 plus to the power minus x. If we take the dx of this, that is dx of sigma x will be the sigmoid function itself, then multiplied 1 minus. Okay, so this can be derived with a mathematical formulation, and there's a detailed mathematical derivation. I will give the link in the description, and this is that derivation from math stack exchange, one of the question here. So you can see that the dx of the sigma x, after doing all this calculation, we arrive at this final form. So in our case, that means our del A11 with respect to del H11 would be A11 into 1 minus A11. Remember, H, the value of H is an input to the function A11. So that's how the sigmoid activation function is calculated. All right, so we are done with number 3 as well. Now we are left with the fourth and final component, which is del H11 and with respect to del W11. That was the last in the chain rule. That was the last component of the earlier expression we saw. So that we already know the value of H11 as we discussed just now. It's the weighted sum of x1 W1 and x2 W21. So let's do that. W11, replace the value of H11, which is x1 multiplied by W11 plus x2 multiplied by W21. And again, if we simplify this, we will be left with x1 here. Okay, so now we got all the 4 components of our earlier expression for the chain rule. So what we just did is this was our chain rule. Let me change the color. So this is our expansion for calculating the rate of change of cost with respect to a single weight W11, and we just calculated now the individual values of these 4 individual partial differential expressions. Now to calculate the final, to get the result of what it means, we just need to multiply all the individual results that we got. So let's do that. So finally, del C by del W11 means the first differentiation was 2 multiplied by y minus y hat. And the second differentiation was just W31. Third differentiation was A on 1, and the final was, sorry, the third differentiation itself was A11 because that was a sigmoid function. So A11 into 1 minus A11. So this entire expression was our third differentiation. That is the sigmoid function. And the last differentiation was just x1. Okay, so this is our final form of del C del W1. So what we can see from this final expression, simplified expression version of this, that we are now able to calculate the impact on the loss value of a small change in the weight value, that is a gradient of the loss with respect to a weight, without brute forcing our way by recomputing the feed-forward propagation for each and every weight. So now with a single step, we can calculate this gradient, that is a rate of change of loss with respect to a rate of change of a single weight. But in our brute forcing process earlier, what we discussed, we had to calculate, if we had million weights, we had to calculate the loss function for each of those million weights. So that would have been hugely much more inefficient. And now the final part of updating the weights for during the backpropagation process. Like we discussed, that the whole backpropagation process is about updating the weight so that the loss becomes lower and lower gradually. So after we get this gradient, so this whole part is our gradient. Now the final weight for we update the weight like this. So updated W is original W minus learning rate LR into this value, that is del C by del WI. Okay, so this W would be I, because we are going through the weights. Okay, all right, that's how the chain rule is implemented. And in this video, my purpose was to arrive at the chain rule, the mathematical derivation of that. In a separate video, we will go through actual Python implementation of the backpropagation process for a very simple neural network architecture. So in the next video, we will take the same neural network that we have here, that is one input layer and one hidden layer, one output layer, and do this whole process of backpropagation by application of the chain rule and Python implementation of the same. Thank you very much. Neural network from scratch implementation with Python. That's the topic of this video. And before we go to the actual Python code, we'll spend a little bit of time on understanding the overall flow and architecture of a classic neural network. So here in the neural network, each neuron is connected to other neurons, but not all connections are equal. Instead, each connection has an associated weight that we can see in this image here, W1, W2, W3. So speaking formally, a firing neuron propagates an impulse of 1 to the outgoing neighbors, while a non-firing neuron propagates an impulse of 0. You can think of the weight as indicating how much of the impulses of the firing input neuron indeed, is forwarded to the next neuron via this connection. Mathematically, you multiply the impulse by the weight of the connection to calculate the input for the next neuron. Like what we are showing in this image, x3 here is a weighted sum. X3 is the value in this node here, is a weighted sum of the input value and the weights of the corresponding input neurons. So we can say that input vectors are fed to the neurons with weights assigned to represent importance. That's what weight is all about, that they represent importance. Calculations performed within the neuron are weighted sum and activation function. So for example, this is a neuron, this is a node, and the calculation performed within it has these two aspects. One is a weighted sum and one is an activation function. And all the weights are coming to this neuron from these input neurons. Let's quickly check weighted sum function in the context of neural network. It is also known as linear combination. The weighted sum function is the sum of all inputs multiplied by their weights and then added to a bias term. This function produces a straight line represented in the following equation. That is, Z is a weighted sum, x1 w1, x2 w2, x3 w3. That's how we calculate the weighted sum here. And For Python, it will be just be an np dot. It's a dot product between the weights and the input values of the input neurons. This is another way to represent it, but this is an activation function. So after the sum of the products of weights and input pairs are calculated, the resultant weighted sum is followed by an additional function, which is called the activation function. And this is what that is being represented here. F is an activation function here. So at a high level, a neural network is a collection of nodes where each node has an adjustable float value, and the nodes are interconnected as a graph of return outputs in a format that is dictated by the architecture of the network. The network constitutes three main parts: the input layer, the hidden layer, and the output layer. Let's quickly go over their definition. Input layer contains a feature vector. Hidden layers, that the neurons are stacked. Hidden layer are layers of neurons, and the neurons here are stacked on top of each other in hidden layers. They're called hidden layer because we don't see or control the input going into these layers or the output. All we do is feed the feature vector to the input layers and see the output coming out of the output layer. And then the weight connection or the edges, for example, all these weights are the edges, that is a connector from x1 to this neuron, x2 to this neuron. So what they are, weights are assigned to each connection between the nodes to reflect the importance of their influence on the final output prediction. In graph network terms, these are called edges connecting the nodes. Yeah, that's right. And the output layer, we get the answer or prediction from our model from the output layer. Depending on the setup of the neural network, the final output may be a real valued output, that is a regression in the case of regression problem, or a set of probabilities, or which is the case with classification problem, either binary or multiclass. So this is determined, the output layer is determined by the type of activation function we use in the neurons in the output layer. So for this example, we have this very simple version of a neural network structure. What we have here, the first layer are the two input layers, and then a hidden layer, and then a single output layer. And this is a fully connected neural network. What we mean by that is that I'm connecting each of these nodes to each of the other ones. So both these nodes has three outgoing connection to these, and this, and then also this node has three outgoing connection to this one, and this one. So there is no skip connection. All are fully connected. And similarly here, there's only single connection here because my output has only a single node. And how I'm getting the value of 1, 1.3, and 0.8 here, that's because of the same thing that we just discussed, that weighted sum. So this one is a weighted sum of the values from initial neuron and the weight. So 1 into 0.8 plus this one into 0.2. Similarly, this 1.3, if you cannot see that, let me zoom it a little bit. So if you cannot, yeah, so this 1.3 is coming from weighted sum of 1 into 0.4 and then 1 into 0.9. You can see that this is the value 1, and I have a 0.9 connection here, and also this is the value 1 here, and I have a 0.4 weighted connection to this node. So I just multiply them and sum them. And so now the concept of activation function and how the output from the hidden layer is calculated. So remember, we already discussed this concept of the activation function here. That is, after the sum of the products or the weighted sum is calculated, that is passed through a activation function. So in this image, this f is an activation function, and that activation function takes as its inputs these terms. This term is a weighted sum, and W0 here represent a bias term, but for the sake of simplicity, I have not included the bias term in our discussion till now. But of course, bias term is a very common in every neural network. We'll come to that in a short while, but for now, just note that this f is an activation function, and that takes as an argument or as an input to the function as the weighted sum. So let's see how this comes out in our neural network. So again, this is a hidden layer, and we already received or already calculated this value 1, 1.3, and 0.8 as a weighted sum. But now we have to calculate the output value from this hidden layer, which is 0.73, 0.79, and 0.69. Let's see how they are calculated. And that's where the activation function comes into play. And we have many kinds of activation function, but these are the most common ones, that is sigmoid, ReLU, tanh, and linear activation. So sigmoid, we will use for this example, we will use the sigmoid activation, which is this expression 1 by 1 plus e to the power minus x. And here x represent the weighted sum that we just calculated. That is, this is the function, and it takes as an input to be passed to the function, and that input is minus this x value. So let's see. And this is the graph representing all these functions. So this is the graph for sigmoid function, this is for ReLU, this is for tanh, and this is the linear activation function. Okay. And now we see the calculation. We already received this value of 1, 1.3, and 0.8 here, referring to this this calculation. That is, 1 is a weighted sum of this, and 1.3 is a weighted sum of 0.4 coming here, and 0.9 coming from here, 0.9 coming from here, and 0.8, this value is a weighted sum of 0.3 coming from this node, and 0.5 coming from this node. So you already have this value. Now that value need to be passed through the sigmoid function, and this is our sigmoid function. So I pass 1 as an input to the sigmoid function of this, that is 1 over 1 plus e to the power minus 1, and get this value 0.73. Similarly, I pass 1.3 as an input to the sigmoid function for this node, and 1 by 1 plus e to the power minus 1, 3 gives me 0.79, and that's what we see. And so for the third node here, I get a value of 0.69. And then the final output value, that is output node value, y predicted, that is a predicted value of y for us. That's again the weighted sum of these values. So the weights for this connection, that is the first hidden layer, first node of the hidden layer to the output layer, is 0.3. Multiply that by the value of 0.73 that we just calculated here with the sigmoid function. Similarly, do for the second node, that is 0.79 we received from here. Multiply that with the weight for this layer, 0.5, and so for the third node, 0.69 that we received here, and multiply that by the weight here for this connection, and I finally get a value of 1.235, which is a predicted value at the output layer. And remember once again that these weights actually represent the importance of a connection. So how important this connection is compared to this connection. So obviously we can see, for example, here 0.8 is more than 0.4. That means this connection is definitely more important than this connection. And the whole idea of forward propagation and back propagation in neural network structure is adjusting or fine-tuning these weights, and we'll come to that in a moment. So this 1.235 is the output value from the output layer, and this is the value that needs to be compared with the actual ground truth, that is actual value of y. So this is my y predicted, and that has to be compared with the y actual. And so the loss concept comes here, that how much of my predicted value differs or varies from the actual ground truth or actual value of y. So let's see, for calculating in the neural network, we have mainly two kind of predictions: categorical variable prediction and continuous variable prediction. And accordingly, we have different kind of losses. So when we calculate the continuous variable predictions, we normally apply these MSE, mean squared loss. And here the yi is the actual y, actual value, and yi hat is a predicted value, and this is the formula for MSE. And when we deal with classification problem, either binary classification or multi-class classification, there the loss calculation is different, and we call it cross entropy. And this is a formula for binary cross entropy loss. That is when we are dealing with a binary yes no or 0 1 kind of variable classification problem. And this is the formula for categorical cross entropy loss when there are multi-class problem for categorical variables. A simple way to visualize the cross entropy loss is to look at the prediction matrix, this image here. So here it's a multi-class classification problem that we are dealing with. We have 1, 2, 3, 4, 5 different classes: dog, cat, cow, hen, and rat in an image classification problem. And the neural network model of ours is predicting the probability that a particular image is a dog or a cat or cow and so on. And these are those probability of predictions. So for example, here on the first line, 0.8, the model is predicting there's an 88% chance, or the probability is 0.88 that a particular image is dog. And in that case, the cross entropy loss is given as below, given as here minus log of 0.88, and which is 0.128. And similarly, we calculate the probabilities and cross entropy loss for various predictions, and we can see that when the predicted probability is more for the correct class, then the loss is less, which is kind of obvious. So now we have gone through the method of losses, the method of the neural network architecture, and the activation function used. So the next step is the main topic of neural network, which is forward propagation and back propagation. So what we learned till now about loss function and calculating weighted average and passing that weighted average as an input to a function called activation function, all these in essence is a feed forward motion or forward propagation. So what we do in basically is at each neuron in a hidden or output layer, the processing happened in 2 steps in the forward movement, which is one is pre-activation and the next one is activation. So in the pre-activation, it is a weighted sum of inputs, that is a linear transformation of weights with respect to inputs available. Based on the aggregated sum and activation function, the neuron makes a decision whether to pass this information further or not. And the activation stage, which is after we calculate the weighted sum of inputs that is passed to the activation function. An activation function is a mathematical function which adds non-linearity to the network, like we used sigmoid function, and there are other like hyperbolic tangent, ReLU, and softmax. So if I have to make the whole feed forward motion in 4 steps, they will be as follows: that perform the sum product at each neuron, then compute the activation, repeat the first 2 steps at each neuron until the output layer, and compute the loss by comparing the prediction with the actual output. So that's in a sense a feed forward motion. So in a nutshell, in the feed forward propagation, we connected the input layer to the hidden layer, which then was connected to the output layer. In the first iteration, we initialized weights randomly and then calculated the loss resulting from those weight values. That was my feed forward propagation. And now the next part, which is back propagation. In back propagation, we take the reverse approach. We start at the loss value obtained in the feed forward propagation at the output layer, last output layer, and update the weights of the network in such a way that the loss value is minimized as much as possible. So backpropagation is exactly the opposite movement in the opposite direction. We start at the end at the output layer and update the weights, continue updating the weights going backward so that my final loss is minimized. And so here the full backpropagation works on a principle of calculus called gradient, and we apply a very famous formula of differential calculus called chain rule to calculate the gradient of all these layers. And I have a separate video on exactly how chain rule is implemented and why chain rule is important, and I'll give the description of that in the this link to the description of this video. So for now, let's go over quickly on the very basic algorithm of the backpropagation, which is there are mainly three steps. Change each weight within the neural network by a small amount, one at a time. Then measure the change in loss when the weight value is changed. That is, we change the weights and then measure the loss, and then update the weight by this factor, that is k minus k and then del L by del W, where k is a positive value and is a hyperparameter known as learning rate, and del L and del W are the change in loss and change in weight respectively. Note a particular point here that the update made to a particular weight is proportional to the amount of loss that is reduced by changing it by a small amount. So intuitively, it makes sense, because if changing a weight reduces the loss by a large value, then we can update the weight by a large amount. However, if the loss reduction is small by changing the weight, then we update only by a small amount. And if all these steps, that is a feed-forward propagation and back propagation, is done once, that's called one epoch. And in a typical neural network, the number of epochs can range from 10, 20, 50, and so on. And also, a neural network contains millions or sometimes even billions of weights and nodes. So calculating this gradient, this value del L by del W, is not always optimal for each and every node, for each and every weight. So we make use of a very handy calculus technique named stochastic gradient descent and chain rule. I have a separate video on that for the backpropagation. I will give a link to that video in the description. So for now, let's go over to the main steps of the whole process. Yeah, so this is the overall steps. In the forward propagation stage, the data flows through the network to get the outputs. The loss function is used to calculate the total error. Then we use backward propagation algorithm to calculate the gradient of the loss function with respect to each weight and bias. Finally, we use gradient descent to update the weights and biases at each layer. We repeat above steps to minimize the total error of the neural network. So now I will pretty much start with a very simple and manual kind of Python implementation for the for our neural network for this architecture. That is, I have one input layer, one hidden layer, and one output layer. And this will not involve exactly all the stochastic gradient descent or chain rule formulas. This Python implementation is just to show at the basic level how a neural network is implemented in code. Later in a separate video, I will go through the exact from scratch implementation of neural network. Okay, so let's jump to the code. So here I am in my VS Code. So first, revisit that the actual algorithm of the whole neural network. I am just copy pasting from my earlier notes and presentation. 1 second. Okay, the high level strategy is as follows: that we perform a sum product at each neuron, compute the activation, repeat these first two steps at each neuron until the output layer, and at last compute the loss by comparing the prediction with the actual output. So first I am going to build a forward propagation function. it is going to be a function that takes in input data, current neural network weights, and output data as the input parameters or arguments to the function, and returns me the loss of the current network state. This function will also have a bias term associated, but I think this just for this function I do not need to worry about the bias terms. When I initialize the weights, that weight matrix will have its bias terms. So for the weights. So first I'm going to calculate the hidden layer values by performing a matrix multiplication, that is np dot numpy dot function. But remember that we calculated the values at each neuron with the weighted sum of inputs and weight values. That's how I connect my input and the input layer with the hidden layer. So and we called it the pre-activation stage, that is before invoking the activation function. I have to calculate these weighted sums, and after these weighted sums are calculated, then I will feed that to the activation function. So I will just rename a variable, long variable name, sorry for that, just to be super clear here. The activation hidden layer value equal to input np dot dots of my inputs and outputs. Sorry, the out it will sorry that's not the output, that's the weights. And I will use weight 0 here because the weight variable will be a full 2 by 2 matrix, or I think that would be, I will initialize the weights at a 4 by 1 matrix. I will detail the weights in a bit. So for now, just remember this weight 0 is my coming from my input layer number 1, and I will also have the bias term, which I will add, that would be WI weights 1. I think it's better if I initialize the weight so that I can be very clear about you can be very clear about the structure of the weights and what they are. So just give me 2 seconds to do that first. Now, before we structure our weight matrix, let's have a quick look in the neural network architecture that we are using for this example. This is the input layer, this is the hidden layer, and this is the output layer. And we need a total 4 list of parameters within our neural network. 2 lists for the weight and bias parameters that connect the input layer to the hidden layer, and another 2 lists for the weight and bias parameters that connect the hidden layer to the output layer. And as I can see that we need this hidden layer will have an output for each of this node. So we need a list to have these outputs as a element of the list, and also the final output layer will have a single value as its output. So now let's get to the structure of our matrix for the weight. And here is my weights matrix. I have generated these numbers with randomly, and included all these np.array numbers inside a matrix. That is, the full thing is a matrix, and we can quickly print this matrix. Print 1 second. So let's print it in a list format. Print w for w in w. weights. Okay, let's run it. What happened? Yeah, it printed the third time. I don't know why. All right, so this is our weight. So the first, this is W0 is this value, the first two list. And then W1 is this, the second one. And this is my W2, and this is W3. Let's print it out, and let's so that we can see properly. Move panel to right. Okay. Print W. Tired of this auto intelligence from VS Code. On W0. Okay. Is it printing? Weights 0. Again, it printed the fourth time. My VS Code sometimes acts crazy. All right, that's weight 0. Let's do this thing for weight 1, 2, 3. Okay, I printed all of them. Yeah, so weight 0 is my, this is my, is a weight 0 is the input layer, is a weights for connecting the input layer with the hidden layer. Input to hidden layer connections. And then this is the bias term for bias terms from for input to hidden layers. And this is also, and weights 2, now I am in the first output layer that would have 3 values. That is the hidden layer, first output layer after the activation function. So these are those 3 values. First, so this is my first output LFYES, and weights 3 are my final output layer value. Final output layer. Final means is the second output layer, second layer. That is, for our case, it is final. Okay. So this is the structure of the weights. So in the feed forward, we need both weights 0 and weights 1 in the feed forward function that we were almost started writing. So because feed forward function is actually calculating the weighted sum between the input layer and the first hidden layer. So, and what are those weighted sums? They are the the dot product of weights and bias terms. So let's do that, carry on with that. 1 second. Okay, so yeah, okay, I was just losing a track. Now I have already calculated the pre-activation hidden value, and now I am going to apply the sigmoid activation function on top of the hidden layer values obtained in these previous steps. That is a pre-activation hidden layer. Invoke my sigmoid. Remember, for this example, we decided to use sigmoid as an activation function. hidden value activation equal to 1 by 1 plus, I'll be using numpy as exp function dot exp, and that would have the minus value, the negative value of this my weighted sum. Pre-activation hidden layer value, right? Why I'm not getting, oh, I have not imported the all the packages. Let's import them. I also need a package called deep copy, because in the next function I will be playing around with the weights, so I don't want to modify the original weight. So again and again I have to create a deep copy of the weights. So copy. For the final plotting, we need matplotlib. SPLT. Okay. All right. That's all the packages we need. Okay. So I'm done with the hidden value post activation. Now I am only left with the actual calculation of the output value and then the mean squared error. Output value. That would be my weighted sum again. Let's call it, I don't know, output value. Equal to hidden value post activation, and I am calculating the, I need the weights matrix again. First output layers and the final second output layer. So I need these two terms for here. Hidden post activation. Weights 2 and weights 3. Okay, output value, yeah. And MSE, that is a mean squared error, is easy. That is just the formula. ID mean squared error. What's the spelling of squared? I don't know. SQUA. Yeah, that should be it. I don't know. I mean, squared error is np dot mean. I need to square the error. So np dot sqi, and between my output value and my outputs. The function originally had output, yes, that's the function I need. And from this feedforward function, I only return this mean squared error. Okay. Yes, so that's my feed forward function, feed propagation function. It takes an input, output, and weights, calculates the pre-activation hidden layer value, invoke the sigmoid, calculates the output value, and ultimately returns me the mean squared error. And remember, our architecture is very simple, so that's why this function is also simple. Oops, I'm sorry, I made a mistake in calculating this output value, that is a dot product between, this will be between hidden value post activation and weights 2 here, and then I have to add the bias term, that is weight 3. Yes, now it makes sense. I think it's better to quickly rephrase these definition of various vectors within the weight matrix so that it becomes clear. So weight 0, this is the weight values connecting the input layer to the hidden layer. So these are weight values connecting input layers to hidden layers. And weight 1, this is the bias terms associated with the hidden layers nodes. Bias term associated with the hidden layers node. Remember, we have 3 hidden layers node, so we need 3 values under weights 1, and that's what we have. These vector here, this vector. And weights 2 is the weights connecting the hidden layer to the output layer. And because we have 3 nodes in the hidden layer, so we need 3 elements under weight 2 vector. So let's rephrase it. That will be weights connecting the hidden layer to the output layer. Okay. And the final one was final is, this is a bias associated with the final output layer. So this is the bias associated with the final or the second final output layer. I think just better to delete the second output layer value. Yeah, now it is much more clear. So now for these output value, the calculation, we need the weighted sum of the hidden value post activation and the final output layer. So that's what we are doing here now. Np dot product between the hidden value post activation and the vector of weight 2, and to that I am adding the bias term of the final output layer. Yes, this makes sense. Now, for understanding it properly, let's keep the code and our neural network side by side. So this is our neural network, input layer here, then the hidden layer and the output layer. So this pre-activation hidden layer value, this variable, I am calculating the weighted sum with np dot. These are these values here. So just like here it is explained with h11 being the pre-activation hidden layer value for the first node, h12 is for the hidden pre-activation hidden layer value for the second node, and h13 is a pre-activation hidden layer value for the third node. And this is just the weighted sum of the weights and the initial input value. So that's this line. Np dot input and weight 0. Weight 0 vector is my weights, and weight 1 is a bias term. But remember that in the image, for the sake of simplicity, we did not keep an image of the bias term, but in actual code implementation we have a vector for bias term as well. So these h11, h12, h13 are calculated by this line of code, and this is called pre-activation hidden layer value. And now the next line of code is invoking the sigmoid function, and that will calculate the hidden value post activation. So let's go to our sigmoid function calculation. Yes, so sigmoid function will take as its input these pre-activation hidden layer value, and that's what this is doing. That this function pre-activation value was 1 for this node, and that is taken in this sigmoid function, and that gives me the result of 0.73. And that's exactly what is being implemented in this line of code, invoke sigmoid. that hidden value post activation value is 0.73 for the first node, and that is being arrived at by uh, invoking the sigmoid function and passing into the sigmoid function our previously calculated pre-activation value. And now finally the output value in the image, that is this value at the output layer. So that is again the weighted sum of these weights, 3 weights and 3 post activation values. So I am getting 0.73 multiplied by 0.3, that is these weights multiplied by these 0.73 value, then this weight multiplied by 0.79, and this weight multiplied by 0.69, and that's what is being achieved by this line of code here. Output value is a np.dot product between the hidden value post activation vector and the weight 2 vector. And remember, what was our weight 2? Weight 2 was the weight connection, the weights connection between the hidden layer to the output layer. Weights connect, yeah, I think I'm just rephrasing it. Weights connecting the hidden layer to the output layer. So this weights 2 vector is these vector, and these vector are all these values. That is 3 weights and 3 vectors. Okay. Yes. So that's my output value. In the image, I got it 1.235. And this 1.235 is a predicted output value from the output layer, and that needs to be compared with the actual value to get my mean squared error. And that's what I'm doing here in the last line of code in this function. That is that's np.mean, and mean is being taken of the square of output value minus outputs. Output is another, this is the real output, actual outputs. Okay, so that should simplify the relation between the neural network image and the code. And the next, we have to actually implement the function for training the weights, that is the gradient descent gradient calculation, and training and updating the weights. Now I'm going to train the weights. With the process of gradient descent. So I'm naming this function just train weights gradient descent, and it will take 4 inputs, 4 arguments, which are the inputs to the network, then the actual output, that is a ground truth, and the weights, and the last one is learning rate, LR. So now first I'm going to create some deep copy of the weights, because at various stages during the training process, I have to manipulate the weights, and I have to deal with the weights in various ways. So I do not want to change or alter the original weights. So I'm just creating some deep copy of the weights that has been given in the argument to the function. So let's do weights. Remember, we already imported this library here, deep copy. It will take weights of the. Yep. And now I initially want to get, before the training starts, I have to get the original loss, because that will be my, remember how the network works, that this training, the whole training is actually the backpropagation, and the whole backpropagation starts from the end and moves to the left through the network. That it starts with the loss from a particular epoch, and then moves backward with the gradient descent process, updating the weights so that the loss gets minimized. So first I have to get the loss of epoch, and that's what I'll do. Original loss equal to, and how do I get the loss? By invoking my forward propagation function, because it returned me the mean squared error. Forward propagation, and it takes inputs, outputs, weights. I think, yeah, I will pass weights original. Yes. All right, and now the actual, I have to loop through the layers of layers and just quickly take a look at our network. I think, yes, this is our network, one input layer, one hidden layer, one output layer. And I'm starting the backpropagation training. That is my current function that I'm writing currently, that starts here, where the loss is generated after the feed forward. And now I just wrote the code for the feed forward function, and I get the loss, and that loss now need to be the guiding point for updating my weights, so that the loss ultimately gets minimized. Okay, original loss, and now for so this function is loop to the network layers. For my layer in, all right, that would be my weights original. And take a quick look at the what was our original weights, because that's a matrix we created it manually, this matrix. And remember that we discussed already that there are a total of 4 lists in this matrix. 1, 2, 3, 4, 4 lists or 4 arrays. The 2 lists for weights and bias parameter that connect the input to the hidden layer, and another 2 lists for the weight and bias parameter that connect the hidden layer to the input layer. Sorry, the hidden layer to the output layer. So weight 0, this is the weight values connecting the input layer to the hidden layer. Weight 1 is for the bias term associated with the connections between input and the hidden node. Weights 2 is a weight connecting the hidden layer to the output layer, and the bias, the final weight one, that is weight 3, this value here, that's a bias associated with the connection between the hidden layer and final output layer value. So now I have to loop through the weights original, and for so these will loop through weights original I layer. The layer will be each layer, and now again I have to loop through the layer index, and here I have to make use of an numpy function called nd-enumerate, which will give me the actual coordinates of each element. And that's because my each layer are of different sizes. Yes, each layer of different sizes, which is reflected in our weights parameter as well. The first list has 1, 2, 3. It's a shape of 3, and the second one also is a single array, and so on. So I have to, yeah, so I have to make use of nd-enumerate. Let's see how it turns out. For index WA weights in np dot nd-enumerate. Quickly check their definition. Multi-dimensional index iterator returns an iterator yielding pairs of array coordinates and values. So, okay, nd-enumerate, and that will take my layer. Now I'm looking through the layer. Again, I am going to store my store a deep copy of original w g. Yes, here where it's temp equal to deep copy weights. Yeah, makes sense. And now the crucial part, I have to update each of the weights. So what I'm doing is I select its index weight, I select the index of the weight, and I add a small value. I will be adding a small value of 0.0001, and because the next loss will be calculated based on this updated weight. We already are given the original weights, and the whole process of backpropagation and the gradient descent is about updating these weights gradually to see how the loss is changing. Updated. Yes. So weights temp, sorry, weights temp, and that would be my this I comes from the outer looping, and now for the inner looping I have to get hold of the index plus equal to 0.0001, and after updating the weights I have to calculate the loss. Calculate new loss after updating weights, which will be, let's define a private variable loss forward. And again, for the loss calculation I have to make use of the forward propagation function propagation, and that would take inputs outputs, and now it will take the updated weights, and that the weight has been already updated, so let's give this here. Okay, and now that my loss is updated, I have to calculate the gradient. So gradient is simply, we calculate the gradient, that is a change in loss value due to the change in weight value. Here the change in loss value is a new loss calculated with updated weights, and the change in weight value is this this number. So just put it in here, loss plus minus change in loss value, the original loss, and divide it by 0.0001. That's my gradient. Note that what I'm doing here above in this line is updating the weight by a small amount and then calculating the gradient, that is change of loss with respect to change in weight. And this is exactly equivalent to the process of differentiation, that is differential calculus, but I'm not making use of any formulas here. Here I'm just doing it very much manually without using the calculus rules. And finally, now that my gradient is calculated, I have to update the weight value. So WIG, make mistake with the weight spelling each time. It's updated. Did I declare this variable yet? I don't think so. Here, let's declare it here. Updated words equal to deep copy weights. So updated weights is originally the deep copy of these given weights, but now I'm actually updating it because I have the gradient and I have the required calculations. So updated. So what's our updated formula? Updated formula is this. Let me copy it from somewhere. So this is our formula that I'm going to implement here, that updated weight is equal to original weight minus learning rate into gradient of loss with respect to weight. So I have the original weight, I have the LR weight given as part of the arguments to the original function here, that is the train function, and gradient I just calculated. So I have all the elements to update the weights. This is I coming from the outer loop where I'm enumerating the original weight matrix all together. And now I have to also get hold of the actual index, which will come from the elan loop. Here, remember here I'm looping through the each layer with an nd.nd and np.nd enumerate. So this should give me the actual respective weights values that I'm talking about here in this part of the calculation. Plus equal to no, that will be minus equal to because original weights minus LR, right? LR into grad. And that should be the whole process of gradient descent for a single epoch. So let's return this value. Return weights updated. And also return original loss for this epoch. Okay. And now I will actually make use of this training process on an experimental set of data set. I'll just be creating a superbly simple NumPy array as my X weights, that is the actual input values from at the start of the network itself, and also a Y value. So let's do that. X equal to, I'm just creating a simple array of 1 1. That's my input layer, as simple as that. And the Y value is, again, I'm declaring the Y values to be 0. Remember, it's a binary classification problem we discussed earlier. 0. So this is my initial so this is my X is the input value in this function and also the feed forward function. Y is the output value. This is the ground to the actual Y value. And from these, and the weights we already discussed in another file. Let's bring this weight variable here in the same file so that we can run all together. So these are my weights. So I already have the inputs, outputs, weights, and the second train function also needs an LR, and that will be default 0.01. So now what I will do is I run the train weights function, that is train weights gradient descent, this function for 100 epochs, and for each epoch I take the loss for that epoch and append to an array. And okay, so let's declare a losses, LOSSES. This array will contain all my losses, original losses from each running through the each epoch while running the train function. And yeah, just remember now this train weights returns me the updated weights and the original loss, and this losses array will have all the original loss for each epoch append to it. Let's do that so that it becomes clear. For epoch in range 100, W loss, this W is actually W updated, loss GNL equal to let's give it a slightly different name, loss original. Yes, train weights gradient descent, and it will take my X, which is my input, and then output, which is my Y, and weights, which is my we this particular variable weights, and the final one is learning rate 0.01. And then I'm just adding these loss value to the losses variable LOSSES and loss for G. So it's simple. This train weight gradient descent function will run for 100 epochs, and for each epoch, it will give me as its return value the updated W and the original loss for that particular epoch. So what I'm doing is I'm just adding these all the losses to an array. And why I'm creating this array, so that now I'll be plotting this array, and I will show that the losses goes on reducing with when the number of epochs goes ahead. That is, for the initial epochs the losses are high, then for with each epoch we improve our losses, that is we reduce our losses more and more. So it will be a reducing graph plot. So let's plot that. ELT.plot losses and ELT.get loss over increasing loss over epochs. Now this is a .py file, so I have to create a Jupyter notebook and then run. I will run it through this whole .py file with a Jupyter notebook. 1 second. So now I have created this empty Jupyter notebook, and in here I'll be running or executing these external Python file where all my codes are. This file, this .py file to run here in this Jupyter notebook. I have to make use of the magic notation of Python. You can check out their documentation. 1 second. Yes, this is a documentation of these %run command in Python. It runs a named file inside IPython as a program, and it takes few parameters like in, I. The I argument runs the file IPython's namespace instead of an empty one. This is useful if you're experimenting with code written in a text editor, which depends on variables defined interactively. So I'm going to use this one. Okay. My file name is neural network from scratch.py. Yes, let's run it. Oops, I'm getting a straight line, horizontal line as my loss over epochs. So these are on the horizontal axis, that's my x-axis is my epochs 0 to 100, and these are my loss. But obviously this is a wrong one, so I must have made some mistake. The loss is not getting updated. So most probably the reason is why the weights are not getting updated. Let's quickly take a look at my code. My final, when I'm running the epochs, from the train weights gradient descent, I'm outputting updated weight and loss original. And oh yes, I found it here. So the mistake was that in this function I was passing the same input weights, but that should not be the case. And that's why, because my weights are not changing, this is a original weight that was passed to the initial epoch to the network, and I'm passing it again and again through these epochs, and that's why my loss is not getting updated. So I have to change it to W updated, and now it should work. Yes, so now we can see that as the epochs are increasing, the loss is continuously getting decreased. So it's a beautiful graph, exactly the way that I wanted it to be plotted. And we can see that after like 80 to 85 epochs, there's no further reduction in losses. So yeah, so that was about this entire video. Thank you very much for watching, and if you think that it's helpful, you can press the like button, or also think of subscribing my channel. Thank you very much.
That pretty much wraps up this video. Stay tuned. My next few videos will all be on OpenCV, image processing, and computer vision. So if you have not subscribed yet, do subscribe. And if you have liked this video, smash the like button. See you in the next video.